In this lecture, I am going to present what is collapse load and what are the basic theorems to calculate the collapse load and what are the different methods of plastic analysis. Then I would like to solve some problems on simple structures by statical method. First, coming to the collapse load. What is collapse load? A structure is said to have collapsed if the entire structure or part of the structure starts undergoing unlimited deformation. This happens when the number of independent static equilibrium equations available is more than the number of reaction components. The state at which this condition develops is said to be collapse mechanism, and the load carried at this stage is called collapse load. The collapse load is also called as ultimate load carrying capacity of the structure. Determine the collapse load of a structure is called plastic analysis. Normally structures are permitted to carry only a fraction of collapse load called working load or service load. The ratio of the collapse load to the working load is called the load factor. The load factor is equal to collapse load divided by working load. Similarly, the factor of safety is equal to the yield stress by working stress. Then coming to the basic theorems for finding the collapse load. There are three basic theorems that help to calculate the collapse load in a complex structure. We know in simple structures there could be only one possible collapse mechanism, and hence not much difficulty is faced in solving the problem. However, in more complex structural problems there can be many number of collapse mechanisms. So we have to investigate all possible collapse mechanisms, and from out of these we have to select a mechanism which gives the lowest load. So there are three theorems on which the plastic analysis has been developed. The first theorem, static theorem or lower bound theorem. Second theorem, kinematic theorem or upper bound theorem. And the third theorem, uniqueness theorem. So what is static theorem? So the static theorem is also called the shape theorem. This is based on maximum principle, and it states that for a given structure and loading, if there exists any distribution of bending moment throughout the structure which is both safe and statically admissible with a set of loads W, the value of W must be less than or equal to the collapse load WC. So in the case of static theorem, that W is less than and equal to WC. The term statically admissible means the bending moment diagram satisfies static equilibrium conditions, and the term shape means at no point the bending moment is more than the plastic moment capacity of the section. This theorem is also called lower bound theorem or shape theorem, since the value of load obtained are always less than or equal to collapse load. So according to this theorem, the load producing a distribution of moments which satisfies the condition of equilibrium and yield is less than or equal to the true collapse of the structure. Then coming to the kinematic theorem, this is also called the upper bound theorem or unshaped theorem. This is based on minimum principle. And this theorem states that for a given structure subjected to set of loads W, the value of W found to correspond to any assumed mechanisms must be either greater or equal to the collapse load WC. So W is greater than and equal to WC. In this theorem, W is greater than and equal to WC. According to the upper bound theorem, the load that produces a distribution is conformity with the equilibrium and mechanism conditions is greater than or equal to the true collapse load of the structure. Then coming to the uniqueness theorem. This theorem is also called a combined theorem because it combines both static and kinematic theorems and which gives unique value for collapse load. That's why this theorem is called the uniqueness theorem. If for a given structure and loading at least one shape and statically admissible bending moment distribution can be found, and in this distribution the bending moment is equal to the fully plastic moment at enough cross section to cause failure of the structure. Due to the unlimited rotations at plastic hinge, the corresponding load will be equal to the collapse load. The uniqueness theorem states that for a given structure and loading, at least one shape and statically admissible bending moment distribution can be found, and under this condition, bending moment is equal to the fully plastic moment at adequate cross section to trigger failure of the structure. As a collapse mechanism due to rotations of the plastic hinge at these sections, that is W is equal to WC. Then coming to methods of plastic analysis. Based on the uniqueness theorem, there are two methods of plastic analysis. First method, statical method or static method, and the second method, kinematic method. Both the methods are based on the important assumptions, that is, once a plastic hinge is formed, rotation takes place freely without any change in the moment acting in the section. This may be represented by moment curvature relation. This is the moment curvature relation. This axis indicates the plastic moment and this axis indicates the curvature. After formation of plastic hinge, the rotation takes place freely without any change in the moment acting in the section. Then coming to the first method, this is statical method. This method is suitable for the analysis of structure for which the shape of the bending moment diagram is easily known. The method consists of drawing statically admissible bending moment diagram and equating bending moment at sufficient points to plastic moment so that collapse mechanism forms. The bending moment will not exceed the plastic moment capacity of the section at any point. In this method, so first you have to find out the bending moment. You have to equate the bending moment with the plastic moment. Then you have to find out what is the collapse load. But in this case, the bending moment will not exceed the plastic moment capacity of the section at any point. Then coming to the second method, kinematic method. Kinematic method is always based essentially on the assumption of a mechanism. Therefore, for the application of this method, it is imperative to know the possible types and number of mechanisms. Generally, there are four types of independent mechanisms, namely the first mechanism, beam mechanism, and the second mechanism, panel or sway mechanism, and the third mechanism, gable mechanism, and the fourth mechanism, joint mechanism. We can combine these independent mechanisms to obtain certain number of composite mechanisms. This method starts with an assumed collapse mechanism. After collapse mechanism is formed, there can be no change of curvature at any cross section except where plastic hinges are formed. Hence, if a virtual displacement is given to the structure just after collapse mechanism is formed, the internal work is done only at plastic hinge where plastic moment MP is acting. So in this method, we have to equate the internal work done by plastic moment at plastic hinge with the external work done by loads. And we have to find out all possible mechanisms, and then one giving the least value may be considered as a real collapse load. This method is also known as mechanism method or virtual work method. Then coming to the first problem, determine the collapse load WC in the simply supported beam shown in figure by statical method. So this is the simply supported beam, and the span of the beam is L, and one concentrated load is present at the midpoint of the beam. This is the figure, the simply supported beam, and this is the bending moment diagram of the beam. Here the bending moment is maximum at the loading point, and the maximum bending moment is equal to WL by 4, and the bending moment at the support is 0. So this is the bending moment diagram of the simply supported beam. So here we have to find out what is the collapse load of the structure by statical method. Since the simply supported beam is a determinate structure, formation of one hinge in the beam creates a collapse mechanism. In this case, so this is the maximum bending moment at the midpoint of simply supported beam. One hinge will be formed, and the collapse mechanism for here only. Since the moment is maximum under the load, the hinge will form at that place. So here the hinge will be formed at the loading point. So we know at the loading, so what is the bending moment here? So the bending moment here is equal to WL by 4. So WL by 4 is equal to the MP. The plastic moment is equal to MP is equal to WL by 4. In this case, in statical method, we have to equate the plastic moment with the maximum bending moment of the structure. Then with this bending moment is both statically permissible and safe, and hinge formation takes place at sufficient number of points to develop collapse mechanism. Hence the W corresponding to equation 1 is a collapse load. So from this relation, plastic moment is equal to WL by 4. So from this relation, we will find out what is the collapse load of the structure. So WC is equal to 4 MP by L. So this is the collapse load of the simply supported beam. Then coming to second problem, determine the collapse load WC in case of propped cantilever beam loaded as shown in figure by statical method. So this is the propped cantilever beam, and the support A is fixed and support B is simply supported, and here there is having a concentrated load W at a distance small b from the support B and small a from the fixed end A, and the length of the propped cantilever is L. So in this case, first we have to make this is a simply supported, and due to this simply supported we can draw the positive bending moment diagram, and due to this fixed end we can draw the negative bending moment diagram. Due to this one, so here the negative bending moment diagram, this is the plastic moment, the maximum moment will get at the fixed end, this is the is equal to MP, but this is the positive bending moment diagram. So the maximum moment is occurs at the loading point. So this is equal to WAB by L. So the height of the maximum bending moment diagram, the maximum moment will get at the loading point. This is equal to WAB by L, and here this portion is MP, plastic moment MP, and this portion is MP. But we have to find out this height by considering this is one triangle and this is another triangle, because this, if this moment is MP and this length is L, and we have to find out this length, this moment, what is the moment at the loading point in the negative bending moment diagram. So this is equal to MP into B by L, because you have to take two triangle here, this is one triangle, this is another triangle. So this by this MP by L is equal to X by B. So X is equal to MP into B by L. what is the total plastic moment here? The total plastic moment is equal to the maximum bending moment at the loading point. At the loading point, the maximum bending moment, this is equal to WAB by L is equal to MP plus MP into B by L. And from this equation, we can find out what is the collapse load, because we have to take what is the maximum bending moment of the prop to cantilever at the loading point, that equal with the plastic moment. Then from that relation, we can find out what is the collapse load by statical method. The prop to cantilever beam form a collapse mechanism if a hinge is found at fixed end and another hinge is formed in the portion AB. In this case, one hinge will form at the fixed end and another hinge will form at the loading point between A and B, that is at the loading point. So here one hinge will form and here another hinge will be formed. Since positive bending moment is maximum under the load, so here this is the positive bending moment diagram. This is maximum under the load, WAB by L. Naturally, the inner hinge will develop at this point because the bending moment is maximum under the load. So the internal hinge will be formed here under the loading. At collapse condition, the bending moment at A and under the load is equal to MP. So what is the bending moment here and what is the this portion, this bending moment is equal to MP at the collapse condition. At collapse condition, the bending moment at A and under the load will be equal to MP. Then we can find out, here we know the maximum bending moment is equal to WAB by L. So here you have to find out the collapse load. So WCAB by L is equal to MP plus MP into B by L. WCAB by L is equal to MP plus MP B by L. Then after simplification, the collapse load WC is equal to L plus P by AB into MP. So this is the collapse load of the prop to cantilever. Then coming to the third problem, determine the collapse load in case of a fixed beam shown in figure by statical method. So this is the fixed beam, we are having the concentrated load W at a distance small a from the support A and small b from the support B, and the length of the fixed beam is L. And this is the bending moment diagram. Due to the support moment, this is the negative bending moment diagram, and due to this load, this is the positive bending moment diagram, and this is the net bending moment diagram, negative, positive, negative. This is cancel, this is the net bending moment diagram. So this is the bending moment diagram at collapse. In this case, the first hinge will be formed at A and the second hinge will be formed at B and the third hinge will be formed under the loading point. At the collapse condition, the moment at support A, so here MP and here also MP and here this is also MP, plastic moment. At the collapse condition, the moment at support A, support B and the positive moment all are equal to the plastic moment. At collapse, the plastic hinge will develop at the supports of the fixed beam and another hinge will develop in the portion AB. So the bending moment diagram is both statically adducible and safe, and at the same time gives rise to plastic hinge at sufficient places. Hence it corresponds to collapse condition, and from the figure, what is the maximum bending moment here under the load? WAB by L, total bending moment under the load. WCAB by L is equal to MP plus MP. This moment MP and this moment is also MP, from the positive moment MP and the negative moment MP. So the total moment here MP plus MP is equal to WCAB by L. So WCAB by L is equal to 2 MP. Then from this relation we can find out what is the collapse load. So WC is equal to 2 MP into L by AB. This is the collapse load of the fixed beam. If the concentrated load is present at the midpoint of the fixed beam, so that case that A is equal to B is equal to L by 2. So if we put here A is equal to L by 2 and B is equal to L by 2, so that case the collapse load is equal to 8 MP divided by L. So if the concentrated load is present at the midpoint of the fixed beam, so that case the collapse load is equal to 8 MP divided by L. Then coming to the fourth problem, a propped cantilever of span L is subjected to a uniformly distributed load W per unit length. Determine the collapse load if the plastic moment capacity of the beam is MP. So this is the propped cantilever, and this is the fixed end A, and this is the support B, and here having the uniform distributed load throughout the span, and the load is given W per unit length, and the length of the beam is given L. This is the bending moment diagram, this is the negative bending moment diagram, and this is the positive bending moment diagram, and after cancelling the negative bending moment, this is the net bending moment diagram, negative, positive. So here also two hinge will be formed, one hinge at the fixed support A and another hinge will be formed between A and B are the maximum bending moment section. So here this is MP, the negative moment at the fixed end, and here also this is also MP, plastic moment under the maximum bending moment, that is also MP. For the formation of collapse mechanism, plastic hinge will be developed at fixed end and at any point in the portion AB. Since bending moment at any point should not exceed plastic moment, the interior hinge will be formed at the point of the maximum bending moment. The interior hinge will be formed at the point of maximum bending moment. Let us take a section at a distance x from the propped end. Find out what is the bending moment at this section. At any section distance x from the propped end, the moment mx is equal to wc into lx by 2 minus wc x square by 2 minus mp into x by L. Here from this moment is equal to mc is equal to wc lx by 2 minus wc x square by 2. What is the load is given here, W, and the total load is W into L or WC into L, and what is the reaction here, WC into L by 2, and what is the moment due to this reaction, WC L by 2 into X, and due to this UDL what is the bending moment, so WC into X by 2, central distance, WC x square by 2. So this the moment by considering the positive bending moment diagram, from the positive bending moment diagram and from the simply supported, so here the moment is equal to mc is equal to wc lx by 2 minus wc x square by 2, but this is the negative bending moment. So here the negative bending moment, this is equal to mp into x by L, because we know at the fixed end the plastic moment is mp and this length is L, and here we have to find out what is the plastic moment. This moment we can find out by considering the two similar triangle. So from these two similar triangle we can find out this height, mp divided by L is equal to this height y divided by x, then y is equal to mp into x by L. Then after knowing this one, so we can find out this one, wc lx by 2 minus wc x square by 2, the bending moment, and here the plastic moment, this is minus mp x by L, minus mp x by L. This is the moment at the section. This is the moment at a distance x from the support B. For mx to be maximum, dmx by dx is equal to 0. Take the differentiation of mx with respect to x and that equate to 0. This one. This is the differentiation of mx with respect to x and is equal to 0. Then after simplification, the plastic moment mp is equal to wc by 2 into L minus 2x. This is equation 1. Since hinge will be formed at x, mx is equal to mp. So mp is equal to wc lx by 2 minus wc x square by 2 minus mp into x by l. Then after simplification, this expression mp into 1 plus x by l is equal to wc by 2 lx minus x square. So this is equation 2. Then substituting the value of mp from equation 1 in equation 2, we get, so after substituting the value of mp here, so this is the expression. Then after simplification of this expression, so here we will get the quadratic equation x square plus 2lx minus l square is equal to 0. Then after solving the quadratic equation, the x value is equal to minus l plus or minus l root over 2. Then the x is equal to 0.414 L. This is the x value. So at a distance 0.414 L from the end B, so here obtain the maximum bending moment. So after putting this value x is equal to 0.414 L, substituting the value of x in equation 1 here in this equation, then we get mp is equal to wc into l square by 2 into 1 minus 2 into 0.414. Then after simplification of this expression, mp is equal to 0.0858 wc into l square. Then from this relation you can find out the collapse load. Wc is equal to 11.655 into mp divided by l square. This is the collapse load of the propped cantilever when subjected to the load of intensity W per unit length. Thus, in propped cantilever subjected to UDL, hinge occurs at a distance 0.414 L from the propped end and the collapse load is equal to 11.655 mp divided by L square. Now all are clear what is collapse load and what are the basic theorems to calculate the collapse load, and what are the methods of plastic analysis. Then how you have to find out the collapse load by statical method of some simple structures.